We're going to take a look at numbers 9, 10, and 11 on the Uniform Circular Motion problem sheet. Number 9, a motorcycle has a constant speed of 25 meters per second as it passes over the top of a hill whose radius has a curvature of 126 meters. The mass of the motorcycle and the driver are 342 kilograms. We're going to find the magnitude or size of the centripetal force acting on the motorcycle and the normal force acting on the motorcycle. This is one I highly recommend drawing a picture for. So here's my hill. You're just a motorcycle going up over a hill. Here's my beautiful motorcycle because I really can't draw. The normal force goes up, force of gravity goes down. Numbers I was given in the problem. Velocity is 25 meters per second. Radius of the hill is 126 meters. Mass, 342 kilograms. I'm looking for my centripetal force. I'm looking for my normal force. Now, we had said that any force that points toward the center of the circle is centripetal force. But what happens when you have a force pointing away from the center of the circle? What do we do then? Well, what we do then is we say the force that points towards the center minus the force that points away is my centripetal force, which is ma. So toward the center minus things that are away from the center equals ma. And I get an equation that I can use to solve for the stuff that I want. So first things first, it asks for what is the centripetal force? Because we don't know what that is. So I look to my equations and I say, well, what equation can I use? I have m, I have r, I have v. So I'm going to use centripetal force equals mv squared over r because I have all the stuff I need on this right side. Mass is 342 kilograms. V is 25 meters per second. Don't forget to square it. Divided by a radius of 126 meters. Plugging into my calculator, I know the centripetal force acting on this motorcycle to keep it in its path of going around this hill is 1,696.4 newtons. Well, what is the normal force? What's that? How much is that going to be? Well, I can take my equation where I know that my stuff towards the inside of the circle minus my stuff going to the outside of the circle equals centripetal force, and I can plug in my numbers. Force of gravity, by the way, I just rearranged this for the normal force, so I add normal over to the right and subtract centripetal force to the left. And I get the normal force equals the mass, 342 times 9.8 meters per second squared, because that's force of gravity, m times g. Centripetal force we just solved for, so I can plug in. And I know the ground is pushing upward 1,655.2 newtons. Now you might ask, what is the point of doing this problem? And we'll be doing a problem a little bit later where we say, okay, if something goes over a hill, how fast does it have to go to catch air or to fly off of this hill? Instead of going down the hill like normal, it's going to catch air and fly off of this hill. What we can figure out, based off of this, we're just sort of going to do it backwards. When the normal force goes to zero, when the ground's not touching you anymore, well, how fast do you have to go to make that happen? And instead of solving for the normal, we go backwards and solve for v. So we're just sort of doing the easier version now so you can see what's happening so that later when we do this, you can get the idea of, oh, we just do the exact same thing, just backwards, and we're solving for v. And then we can figure out how fast you have to go to fly off of a hill, which is a bad idea. I don't recommend it. Okay, moving forward with number 10. Number 10, a roller coaster at an amusement park has a dip that bottoms out in a vertical circle of radius r. A passenger feels to see the car pushing upward on her with a force equal to twice her weight as she goes through the dip. If the r is 20 meters, how fast is the roller coaster traveling at the bottom of the dip? Another good one to draw a picture for. So the roller coaster had a big hill maybe that was up here, and you go down, and then you're about to go up another hill. When you get down here, you feel like you're being squished into your seat, and the forces acting on you are gravity downward and the normal force up. Radius of the turn, or the hill here, is 20 meters, and the normal force, we don't know what it is, but we know that you feel like you weigh twice as much. You feel you're experiencing 2 G's of force, or you feel like you weigh twice as much as your normal weight, or 2 times the force of gravity. Well, how fast are you going? This is an important thing for roller coaster designers because if this gets too big, if your G forces get too high, you can make people feel very sick, get hurt, or pass out, and we don't want that. So they specifically design roller coasters at the bottom of hills and the top of hills to have you experience particular G-forces. Well, if they know how big they want the roller coaster to be, they can figure out, well, how fast do we need you to go? And that's what we're doing in this problem. So the normal force is what's going towards the center of the circle, so that's positive. Force of gravity is going away from the center, so that one's minus. It's reverse of what happened last time, but it's towards the center, minus away from the center is my total centripetal force. So what equation do I want to use to try and solve for some of this stuff? Because I'm trying to solve for the velocity. I know my normal force. I know force of gravity is mg. So what can I do here? Well, I'm going to use centripetal force equals mv squared over r, because v is what I'm looking for, so I better have it in my equation. I know my centripetal force is normal minus gravity, so I'm going to plug that in. Normal minus gravity equals mv squared over r. Well, I don't know what normal force is exactly, but I know it's 2 times my force of gravity, so I'm going to plug that in. Normal is 2 times my force of gravity. I'm experiencing 2 g's of force. So 2 times force of gravity minus force of gravity still is mv squared over r, because all this stuff over here is just centripetal force. Well, 2 f of g's minus f of g, and I'm going to plug in what f of g is, which is mg and mg. So 2 mg's minus an mg is just 1 mg, because 2 of them minus 1 of them is just 1 of them. So mg equals mv squared over r. And my m's cancel, because I have it on both sides, so I can divide them out. And I get g equals v squared over r, which I wrote over here. And I'm solving for v. So I'm going to multiply r over to the left and take the square root to get rid of my squared. And I'm going to plug in some numbers. So the square root of g, 9.8 meters per second squared, times the radius, which is 20, is going to give me my speed. So if I'm going to experience 2 g's of force, I'm going to have 14 meters per second worth of speed to make that happen. Finally, number 11. Number 11 is another challenging one, which a 2,100 kilogram demolition ball swings at the end of a 15-meter cable on the arc of a vertical circle. At the lowest point of the swing, the ball is moving at a speed of 7.6 meters per second. We're going to find the tension in the cable. Hint, hint, do not forget to add tension and gravity to find centripetal force.